Howdy crew! In this video we're going to take a look at what's called Newton's method. It's a way for us to solve tricky equations that other algebra methods don't allow us to use. And you've seen something similar to it before, and it's going to make a process we've worked on before a heck of a lot easier. So in this lesson we're going to do a quick review of differentials and what a linear approximation is, and then we'll investigate why Newton's method works and give some examples. First things first, let's see if we remember this kind of question. Use the intermediate value theorem to show that that equation has a solution on the interval from -1 to 0. Now that part wasn't too hard, plugging in -1 in for x, plugging in 0 in for x, and show that their signs were opposites. But if I ask you to figure out what that solution is, we would have to narrow down this interval over and over and over again until we found a combination that worked. A long process taking way too long. Instead, let's use our knowledge of differentials. So recall this formula that we worked on in our last lesson, f of a plus f prime of a times dx. Now if you notice this where it says x sub 0, that's going to be my original known point. So we want to call that our known point. And from there I added in our triangles that we worked on in our last lesson. Our dx, our distance from that known point, and our dy, the distance of it changing. And if you notice, the hypotenuse of this right triangle is the tangent line with its slope. Now the only change that I made is I extended that tangent line. I extended that blue line all the way down to the x-axis, where it says x1. This x1 is the root of this tangent line. What we're going to end up doing is we're going to end up taking this equation and making some small edits and see what happens when we do. The first small edit I'm going to make is that instead of saying f of a, I'm going to change that a to x sub 0. We use that x sub 0 notation. That's showing us the starting value for x. This is our starting x. Plus that f prime of x sub 0. And the dx I'm going to make a little edit as well. The edit I'm going to make here is, I'm really looking at the distance between x0 and x1, those two x values. I know my picture up here is a little bit different. What we're really doing is we're finding the distance between the x that I started with and whatever my result was. Now using that formula, we're going to be able to figure out something interesting. You notice again, we're going to be interested in these solutions down here on the x-axis, where these tangent lines hit the x-axis. And you know from your Algebra 1 and Algebra 2 days that in order to figure that out, I'll need to set that equation equal to 0 to figure out where those roots are. Now let's see what happens when I play with this equation a little bit. What I'm going to do is I'm going to try to get x1 by itself, and you'll see why in just a moment. In order to get x1 by itself, I would need to have to take away this f of x minus 0, or f of x sub 0. Still want to get rid of this f prime, so I'm going to divide by that on both sides. And here's what that looks like. If I can divide both sides by f prime of x sub 0, you cancel it out. And the last bit of canceling I can do is add that x sub 0 back. And when you do that, you get this formula. Now, what does this formula allow you to do? You might be wondering. Well, that's where this Newton's method comes into play. Named after, of course, Isaac Newton. It's really an iterative process. When I say iterative, I mean we're going to take this one step at a time using our answer to produce the next one. So our first step in this process is to choose an x value. So I'm going to choose an x sub 0 that's close to the root that I am looking for. Whatever one turns out to be close. And what we're going to do is we're going to evaluate all of these little pieces. We're going to have this piece, this f of x sub 0, that's just going to be plug in. We're going to plug in to the original function. On the bottom, where that f prime is, we're going to plug into the derivative. Once you plug the numbers in, you're going to get a new x value. This x sub 1 is a new x value. If you notice this picture, if I go back to the picture, notice how this x value, x1, is getting ever closer to the actual root that I'm interested in. Every time we go through this process, we use the new x value to get even closer, to get x2. If I did it again, draw a new tangent line there, I would get an x3. And I would get closer and closer and closer until I got to the one that I want. And what we're going to do is we're going to repeat the same procedure for this new x value until I get the same answer twice in a row. If I get the same answer twice in a row, that means I've arrived at the answer I'm interested in. So let's see how this works. Use Newton's method to find the real root of this function accurate to 3 decimal spaces. I'm going to have to figure out what number is going to be close to our potential answer. And it turns out that x equals 1 is a close enough answer that we can start with. So that's going to be my x sub 0 is going to be 1. Now to find x sub 1, we're going to use our formula here. This Newton's method formula says, here's my starting x value, and I'm going to subtract what I've evaluated the original function. So in this case, 1 cubed plus 2 times 1 minus 6, all over the derivative with that number plugged in. So it will be helpful to find our derivative, of course, having that just off to the side. Of course, using the power rule, I get 3x squared plus 2 as a derivative. So on the bottom of this fraction, I'm going to take out the x's and put in a 1. Now our job is to evaluate that. And we'll see what our x value turns out to be. So here Desmos is going to be our friend, being able to type all of these in accurately and to be able to change some answers when we're ready for it. Plus 2. Now once I've done that, I've gotten this 1.6. This 1.6 is my x1. That's my approximation getting closer and closer and closer to the actual answer for this problem. Now x sub 2, I'm going to follow the same procedure I just did. But instead of plugging in a 1 in for my x's, I'm going to put in 1.6. 0.6 to the third. Plus 2 times 1.6 minus 6. All over that. Now once I do that, it's just going to be a matter of copying and pasting. We're going to follow the same procedure, but instead of a 1, we're going to put in 1.6. And we'll see what happens. If you notice, our value is getting a little bit closer. Now, this decimal is starting to get nasty. But again, I'm still going to follow the same process. Instead of that 1.6, I'm going to put in this value. Now, if you noticed, I used the entire decimal. And my answer for that x sub 3 is a little bit different than what we just had. We're going to follow the same procedure again. And remember our rule, we're going to follow this procedure until our value here is the same for the first 3 digits. So I can go through. It's going to be the same process, but instead of that 1.466, I'm going to plug in my 1.456 all the way through. And we're going to see what happens. I want you to notice something here. In these two answers, after we've gone through this process, these answers are identical up to the first 3 digits, 1.456, for both of them. Now beyond it, it's not exactly the same, but for this question, we're trying to go to 3 decimal spaces. So to show your work for this, my expectation for you is that you've shown me the first example, and probably the second one as well. Once we get started into the nasty decimal range, we're going to show our numerical setup and then our final answer. So in this case, our final answer to 3 decimal spaces is 1.456. Showing the setup for the first couple, and then using our calculator to help us get to our final answer. Now some conclusions here. This is just going to be a formula plug and chug sort of idea. If we know this formula, our original x minus plug into the original over plug into the derivative, and we're going to continue to use that process all the way until I've got my answer down to the recommended number of digits. Now, the reason why we study this procedure converges to an answer very quickly. If you look at this last example, it only took us 4 rounds. 1, 2, 3, 4 rounds to get an answer that was accurate to 3 decimal spaces. If I needed to go more, I could. It would only take an extra round or 2. The reason why it's useful is calculators and computers use this all the time in order to store some information. We're actually going to go over what they actually do in class. But for now, understanding we have this formula that we're going to be able to use and continue to iterate it until you've got the answer you're looking for. Nice job.